So we are talking about the analysis of algorithms. So we said that we are interested in measuring up to orders of magnitude, and we are looking at this asymptotic complexity. So we want to know what happens as n becomes large. So we would like to say that n cubed eventually grows faster than 5000 n squared. So we now want some way of writing this down precisely. How do we argue or how do we describe the fact that f of n is a bigger function of n than g of n? So how do we compare functions so we can say this algorithm is better than that algorithm asymptotically? So in order to compare one function against another function, we have this notion of an upper bound, right? So this big O notation, as it's called, so this big O, so this O here is a capital O and it's called big O. So we say that f of x is big O of g of x if in some sense g of x sits above f of x. Now because we are ignoring constants and orders of magnitude is what matters, we are allowed to make g of x sit above f of x by multiplying g of x by some suitable constant. And like we saw with that n cubed and n squared example, this may not happen initially. So you might need to go to large enough n for this to happen. So you basically need to find two values. You need to find an x naught and you need to find a c, such that if you go beyond x naught, then f of x is below c of g of x. Right? So if you want to write it more mathematically, you say that for every x bigger than or equal to x naught, f of x is smaller than or equal to c times g of x. So you have to find, to claim that f of x is over g of x, you have to find, so g and f are given to you, right? You are told what is f of x, you are told what is g of x. The question is g of x an upper bound for f of x? In other words, f of x in general smaller than g of x as a function of x. So for this you need to find these two constants, c, the multiplier for g, and x naught, the threshold beyond which this holds. So here is a picture on the right. So this is our f of x, okay? And for some suitably chosen g, this is our c times g of x, right? And this at this point is our x naught, right? So if you believe that this function continues to behave similarly to the right beyond what we cannot see, you can see that in this interval the relationship between f and c times g is a little bit ambiguous. Sometimes f is below g, sometimes f is above g. But once it crosses x naught, you have this property that f of x is always below c times g of x. So this means that in such a situation I can declare that f of x is big O of g of x. Right? So just to give an idea about how these, so basically it's saying that one graph is above the other graph. That's what we're saying really if you draw it, right? So here are some of the graphs that we talked about when we saw this table of functions. So here is a particularly simple graph which is just a constant function. So this is so not many algorithms have this kind of constant behavior, but you can imagine an algorithm which takes a list and returns the first element of the list. So it doesn't really matter how large the list is because it's always going to just pick up the first element which is available and give it to you. Right? So this is a typical example of an algorithm which takes constant time. Its input doesn't matter. So then you obviously have a straight line at the bottom, right? Now log n is kind of hugging the bottom, it doesn't grow very fast. Square root of n also doesn't grow very fast, but it grows faster than log of n. So square root of n is actually an upper bound for log of n. So you can say log of n will be big O of square root of n, but not vice versa. This is our y equal to n, where I have a straight line which is kind of at 45 degrees. And now n log n it looks almost like a straight line, okay? But it is basically, at this scale it looks like it's closer to n squared, but as this line grows up, you can find out that n log n is much closer to n than it is to n squared. So n squared is this parabola, n cube we have not drawn. 2 to the n is even steeper than n squared and n factorial is even steeper than 2 to the n. So this we saw in the table last time and now you can see it in the graph. So in big O sense, each of the lower curves is going to be in big O of the upper curve. So what I said before is that to show something formally is big O, you have to demonstrate these two constants c and x naught. So let's do a couple of examples and then we will see a simpler way of doing it informally. So let's look at two functions, 100n plus 5 and n squared. So I want to argue that 100n plus 5, so this is my f of n, right, and my g of n is n squared. So I want to argue that f of n is big O of g of n, where g of n is n squared. So I need to find this constants. So I do a little bit of manipulation. I look at 100n plus 5 and I say that okay, 5 will be less than n if n is bigger than 5. So if I take 100n plus 5 and instead I write 100n plus n, then the right hand side is going to be bigger than the left hand side provided n is bigger than 5, right. So I choose n bigger than 5, then I have 100n plus n, but 100n plus n is nothing but 101n. So 100n plus 5 is less than equal to 101n. Since n is always positive, remember we are looking at functions where n describes an input size, and obviously the input size is not going to be negative or something. So since n is only going to be positive, 100n is 101n for n bigger than 5 is going to be smaller than 101n squared, right. So therefore, if I take now 101n squared, it is of the form c times n squared, and n squared was the function I was looking at. So basically my constant that I have discovered is 101, and the lower bound beyond which this happens is 5. So n naught is 5, right. So for all, what we are saying is for all n greater than n naught, which is 5 in this case, 100n plus 5 is less than equal to 101 times n squared, right. So this is the kind of analysis that we have done to show that 100n plus 5 is big O of n squared. Now it turns out that this is not unique. I mean, this choice of c and n naught really depends on your cleverness at finding out how to establish this, and there may be more than one way to do it. So for the same example, right, instead of writing 100n plus n, I could write 100n plus 5 times n. That is also true, except now it becomes true even for n bigger than or equal to 1, because once I have n equal to 1, 5n becomes 5. So this is 5n, which is 5, and this is 5, so they are the same. And if I go to something like 2, then 5n will become 10, and so this right hand side will become larger than 5. So therefore for n greater than 1, we have 100n plus 5 is smaller than 100n plus 5n, and now if I combine these two, I get 105n, right. So now I have a different choice. I say now if I take any for all n bigger than 1, right, I have that f of n is smaller than or equal to 105 times g of n. So now I have a different n naught and a different c, right. So this is one way of doing this, and it shows that the choice of n naught and c is not unique. Now let us look at something where both sides have the same kind of highest degree. So we have here a quadratic 100n squared plus 20n plus 5, this is our f of n, and we have another quadratic which does not have any coefficients, does not have any linear terms and so on, just n squared. But I still claim that 100n squared plus 20n plus 5 is big O of n squared. So again you can do a similar trick, you can kind of convert all of these into n squared form. So you can say that for n bigger than or equal to 1, there is 100n, 20n I multiply by n to get 20n squared, 5 I multiply by n squared to get 5n squared. So I get that this whole thing is smaller than 100n squared plus 20n squared plus 5n squared. So if I combine that, I get 125n squared, right. So now we can say that the left hand side, though it has a kind of a bigger coefficient for the n squared term and it has these linear terms, it is still below 125 times just n squared. So the left hand side is big O of n squared, right. So what really matters in some sense is the highest term. So what we are saying is that any polynomial in which the highest term is 2 is big O of any other polynomial whose is basically big O of n squared. So n square is as big as any polynomial of degree 2 in this order of magnitude notation. So in particular we have this constant 100 which does not matter. We also have this extra linear term which is going to be dominated by the quadratic term. So all these things go away. So really we are looking at the highest power when we are comparing say polynomials, then the highest power is what matters, right. So by the same token, if I look at n cubed, then it cannot be n squared, O of n squared, because if it is O of n squared, then I will get something like c times n squared, and I will want n cubed to be less than c times n squared for all n above a certain thing. But we know that once we cross c, remember we saw the particular example with 5000 n squared right at the beginning. So once we cross c, n cubed is going to get higher than c times n squared, no matter what c we choose. So we can never find such a c, and so something with a higher power n cubed can never be big O of something with a smaller power. So the simple rule of thumb is you just look at your function, especially when it has polynomial terms, and you can look at the highest power and decide based on that. And of course sometimes it is more than just a polynomial, it could be something like n squared log n or something. So now n squared log n would be smaller than n cubed because log n is smaller than n. but n squared log n will be bigger than n squared and so on. So you can do a rough and ready big O calculation, but to formally verify it you have to go through this mechanics of using the constant and finding the minimum level beyond which it holds. So one of the useful properties of this big O notation is that if I add two functions, then they lie below the maximum of the two in terms of big O. Right. So we will see why this is important. So supposing I have a pre-processing step, like for instance in the Aadhaar card example, this is my sorting step, okay, and then I have an actual computation step. This is a search all SIM cards. Right. So now I might do some kind of analysis and get some F1 as the complexity of that, and I might do some analysis and get F2 as the complexity of this. So I have two different algorithms, one which sorts the cards and one assumes the cards are sorted and then compares. Right. So the total time that I want to reason about for this algorithm is F1 plus F2, because I first have to do F1 work, then I have to do F2 work. Right. So that's what this is saying. So F1 of n plus F2 of n. I've taken input, I first do F1 work and then I do F2 work. What can I say about this if I know something about each individual step? Right. So in each individual step, I know that F1 is within G1 of n and I know that F2 is within G2 of n. And the claim is that the whole thing F1 plus F2 is within the maximum of G1 and G2. So it will not exceed the maximum of G1 and G2. So why is this the case? Well, just from the definition, we know that F1 of n is below C1 times G1 for some n above n1, and it's below F2 is below C2 times G2 for n above n2. Right? This is just the big O definition being stated concretely for F1 and G1. So I have these four constants C1, C2 and n1, n2. So what I will do is I will take the maximum in each case. I will let C3 be the maximum of the two Ci's, C1 and C2, and I will let n3 be the maximum of n1 and n2. So now I want to look at what happens for F1 and F1 plus F2. So I will look above the maximum. So I will look above n3. So since I am above maximum of n1 and n2, I know that F1 is below its upper bound, and I know that F2 is also below its upper bound because both of them have already crossed their threshold, because n3 is bigger than n1, n3 is bigger than n2 because it's the maximum of the two. So for both F1 and F2, I can use this fact, right, that they are big O, and get this inequality saying that they are below C1. Okay. Now because C3 is bigger than both C1 and C2, I can write this as C3G1 plus C3G2, right. This is also valid because if it is smaller than C1 times G1, it is smaller than C3 times G1 because C3 is even bigger than C1, same with C2. So if I take that C3 and then I collapse it, I get C3 times G1 plus G2, right. So I am just doing some simple algebraic manipulation here. So I have taken C3G1 plus C3G2 and collapsed it into C3 times G1 plus G2. Now I have this G1 plus G2, right. So in general, if I have some two values x and y, right, if I take the bigger of the two, let us assume that y is the bigger of the two, then I will have y plus y, right. So I claim that x plus y is always going to be smaller than 2 times the maximum of x times x and y. Right? Because instead of the smaller value, I put the maximum. Instead of the bigger value, it is itself the maximum. So that's 2 times the maximum. And what I started with is smaller than that. Right? So therefore, this is going to be less than 2 times. So C3 times this is there, and I'm going to replace this by 2 times the maximum. So now with our new constants 2 times C3 and N3, I have shown that F1 plus F2 is big O of max of G1, G2. So going back to our earlier discussion about that SIM card, Aadhaar card case, the importance of this is now when I have these algorithms which take multiple phases and I analyze each phase at a time. So I tell you that the first phase takes GA of phase A takes order of GA time and phase B takes order of GB time. From this I can conclude that the algorithm as a whole takes a maximum of order of GA and GB. Right? So in practice what this means is that each individual block contributes some time and the largest of these blocks dominates the overall running time of the algorithm. I don't have to add them up and get some new number, right? It's the maximum of the running time of each block or each phase. So the least efficient phase is the bottleneck, right. So this is what we are saying. If I have to do a sequence of steps, right, and for each step I have calculated this asymptotic complexity individually, then to get an estimate for the whole algorithm, I can take these steps and find the worst step, worst section, and say that that dominates. So that makes it much easier to analyze algorithms, because I can now break up the algorithm into blocks, and I can say, okay, this block takes so much time, and after this block ends it goes to this block. So this block takes so much time, so it's F1 plus F2, but then the maximum of these two will dominate the running time. So this is for upper bounds. Sometimes we might want the other way. We want to say that a function is above another function, right. So this is called a lower bound. So earlier we said that fx is below gx, now we want to say fx is above gx, right. So this is written using this Greek letter omega, capital omega in particular, right. And so similar to the other one, you want to find these constants, but here instead of saying that f of x is smaller than or equal to g of x, you are saying f of x is bigger than or equal to g of x, right. So this says that now g of x is a lower bound, right. It is saying that f of x will never go after a certain point. If I know something of g of x, I know f of x is always above. So it's going to take at least so much time. If I can say, that's what you say for a lower bound. It cannot take less than so much time. So if g of x is some known quantity, it will say f of x, I don't know what it is, but it is big omega of g of x. It cannot take less time than g of x. So here is an example. You can say that, remember we said that n cubed cannot be big O of n squared, but n cubed is omega of n squared, because simply put, n cubed is bigger than n squared for all n, right. So if I just take trivially my horizontal limit to be n equal to 1 and my constant factor to be 1, I get that for every n bigger than 1, n cubed is bigger than n squared, and so n cubed is n squared is a lower bound for n cubed. Now this is not something that we typically establish for an algorithm individually, right. We don't say that this algorithm is a lower bound for that algorithm or something like that. Rather what we say is that for a problem as a whole, I must take at least so many steps. So this is a lower bound for how many steps of work this problem requires to be solved. For example, right, if I take an unsorted sequence and I ask you to search for a value which is not there, I claim that no matter how you do it, whether you scan it from left to right, right to left, okay, whatever way you do it, if you don't have any particular structure to the order of the values, there is no way to determine that a value is not there without examining every value. So I can then argue that searching for an element in an unsorted list, I mean this is what I gave you as an informal argument, but you can formalize this to say that searching for a value in a value which does not exist in an unsorted list is going to have a lower bound of the size of the list. Unless I look at every element, I cannot conclusively declare that this value is not there. Okay. A similar example happens in sorting. Now in most sorting algorithms that we will see, the way that you sort is you compare two elements in an array and you want to put it in a particular order, say ascending order. You want the first element to be smaller than the second element, and if it is not, you exchange them. So this compare and swap. So you compare two elements. So what you are allowed to do to sort an array is usually to compare elements and to rearrange them. So in this model where you are comparing and rearranging, it turns out that you need to compare at least n log n times. So this is a problem, this is a lower bound for sorting as a problem. So it says that no matter how clever your sorting algorithm is, you are not going to be able to use this compare and swap type of algorithm and get away with less than n log n comparisons, because that is a lower bound, right. So independent of whatever algorithm we choose. So the same thing with the earlier thing about searching for a value which is not present in a list. Independent of how you scan an unsorted list, whatever strategy, you look at all the odd positions and all the even positions, you look at left to right, right to left, you start in the middle and go forwards and backwards. All of these are going to have to force you to see the entire list, so you cannot do better than order n time. Now in some rare situations, we are able to actually show that there is a lower bound for the algorithm that I am trying to solve, for the problem I am trying to solve, and I have an algorithm whose upper bound is actually the same as that lower bound. So this is what is called a tight bound, and it is written theta, right. So as you would expect, what you want is the same function, like you want to say that I have the best possible sorting algorithm. So if I argued that n log n is a lower bound for the number of comparisons, and I do have an algorithm which performs in order n log n comparisons, then I have something which is effectively the best I can do, because it does as many comparisons as is required and no more, right. So you want the same function, in this case n log n, right, to be both an upper bound and a lower bound. So you want to say that there is a constant such that f is bigger than c1 times g, and there is another constant such that f is smaller than c2 times g. In which case now f is sandwiched, basically it is essentially the same as g, right. So here is a simple example. So we want to claim that n into n minus 1 by 2 is actually theta of n square. So we have to first show that there is an upper bound, and then we have to show there is a lower bound. So here is the upper bound, right. So I just take n into n minus 1 by 2 and I expand it, so I get n squared by 2 minus n by 2. Now because n is positive, I am subtracting some positive quantity, right. So in the worst case I am subtracting 0, but when n becomes 1 I am subtracting half, n becomes 2 I am subtracting 1. So I am subtracting something positive from n squared by 2. So if I do not subtract, I get something bigger, right. So n squared by 2 minus n by 2 must be smaller than or equal to n squared by 2. Right. So I am now claiming, I am looking for something with respect to n squared. So I claim that this factor half is my multiplier that I want. So for all n into n minus 1 by 2 is going to be upper bounded by half times n squared. Conversely, if I do the lower bound, right, I do the same expansion, and now I say, okay, instead of subtracting this, I subtract more. So I subtract n by 2 times n by 2. Now n by 2 times n by 2, if n by 2 is a fraction, when you square it, it becomes smaller. Half squared is 1/4, 1/4 squared is 1/16. So numbers smaller than 1, when you square them, become even smaller. But numbers bigger than 1 become bigger, right. So long as this quantity is bigger than 1, n squared, n by 2 whole squared is going to be bigger than n squared, right. So this is the same thing as saying that n is bigger than or equal to 2, right. So for n bigger than or equal to 2, if I subtract n by 2 times n by 2, what I get is something where I am subtracting more than I am subtracting here. So this quantity is bigger than this quantity, right. So this is what I need for an upper bound. But what is this quantity? This is n squared by 2 minus n squared by 4, which is equal to n squared by 4, right. So we are saying that n squared by 2 minus n by 2 is bigger than 1/4 n squared. So I have another constant now, 1/4. So now with these two constants, basically I have that 1/4 of n times n squared is smaller than n into n minus 1 by 2 is smaller than half n squared, right. So this is the form in which I want this thing to show that this is theta, okay. And what is my value? Because in one case I need 2 and one case I need 0. If I choose n to be bigger than 2, both of these inequalities will hold. So to summarize, we saw these three notations to compare functions. So big O is an upper bound notation. So f is big O of g if g is an upper bound for f. So beyond a certain point, some constant times g is always sitting above f, and this is useful to describe upper bounds for worst case running time, right. For problems as a whole rather than individual algorithms, sometimes we would try to establish lower bounds. You must do at least so much work, no matter how you try to solve it. So it's not very useful to establish a lower bound for an algorithm individually, but for a problem as a whole, and this is given using omega. You just invert the condition. You say beyond a certain point, f is always bigger than c times g. And finally, you might have a situation where you have a matching upper and lower bound, and this is a tight bound. And if it so happens that you have an algorithm whose upper bound matches the known lower bound for the problem you are trying to solve, then you are in good shape because you have actually found an optimal algorithm for that problem.